well. There wasn't. The good thing is there wasn't anything that was consistently missed. Although on 25, and 25 was actually based upon the last problem on the test was actually based on a true story. I was driving where I was at in Africa. You didn't see like the big herds of elephants, so you had to drive about 4 hours north to get to this place called the Chobe Game Park. And so some good friends of mine were up there, and it was cool. They taught the middle school that they taught at was like literally like right beside the game park. And so they'd be teaching, and like they'd see like an elephant literally just walk through the school. They're like, not a big deal, you know. Like, nah, just, you know. So anyway, so I was driving up there to see them, and thankfully it was like a full moon, and it was a pretty heavily wooded area, and they had cleared the brush back on each side of the road, and it was like 11 o'clock at night, full moon. Out comes this, one of the biggest bull elephants I ever saw the entire time that I was there. And thankfully it was a full moon, so I saw him ahead of time and had time to stop. Because here's a general word of advice: don't hit an elephant with your car. You will lose. Just saying. Because you think hitting deer is bad, imagine hitting like, you know, an elephant goes right on top of you. It's not pretty. Anyway, so thankfully it was a full moon and was able to stop. Or otherwise we might not be here having this discussion. So, anyway, so other than that, anybody have any questions? Like I said, oh no, the test went pretty good. Going once, going twice. So, give me the test back. Sir? Peter? What is it? How much variation can you have on the page?
That was good. I like that.
Okay. So here's where we're at right now. So start that up.
It's going.
Oh, okay. All right. Never mind. So here's where we're at. So we got through the beginning. Math toolkit, we had to do physics. Then we went from there into velocity. Okay. Frame of reference, displacement, all that good stuff. And so now we're going to look at what happens when you change velocity, otherwise known as acceleration. So this is like this middle of this trifecta. So we did velocity, got done with that. Now we got acceleration. And then once we figure out acceleration, then we can do forces, because force equals mass times acceleration. So if you can't calculate acceleration, you can't calculate forces. Okay, so that's why you kind of have to go in this sequence. Now, how I approach acceleration is a lot different than anybody else in the world, because I actually start with the lab dealing with acceleration, and then we'll figure out the equations later on. Because if you can't conceptually get what acceleration is, then the equations don't mean anything. Okay, so that's why I always start with a lab first. Now, here's the first thing that I have to stress again, is that acceleration is not how fast you are going. Okay? It's not how fast you go. It's the rate at which your velocity changes. Just because something has a small acceleration doesn't mean that you can't make it go fast. Okay? You look at like the Saturn V rocket that got the Apollo mission to the moon. Okay? The acceleration off the launch pad might have been 2 or 3 meters per second squared. But if you apply that acceleration long enough, you can go really, really fast. And just because something has a really, really big acceleration doesn't necessarily mean that it's going to go fast. Because if you have a really, really big acceleration, but it only occurs for a very short amount of time, you don't see a big change in velocity. So you can have the same change in velocity occur very rapidly or over a long period of time. But you can still end up at the same velocity. So get out of your minds right now that acceleration is how fast you're going. It's a rate function. That's why it's meters per second or meters per second squared. It's a rate function, okay? Now, So what we're going to do in this lab is we're going to kind of basically simulate a very, very weak gravitational field. So give that a spin. So here's all you have to do in the lab itself. So you take a cart, okay, and make sure you do this with the wheel side down. Don't do it like that. Okay? It's not going to end very well. So you're going to put it on here, and it's kind of a low friction deal, right? So you can do this. Okay? Hours of entertainment pleasure. And with these ramps, you'll notice that there's like a 0 end, and then there's like the 120 something end. The 120 something end is the one that you want up in the air. So you can take a block of wood, it doesn't have to be a big angle, and you set it up like that. Life is good. And you take the cart down here, doink, give it a push. Oh, not that hard. Give it a push. Have it go up. Oddly enough, comes back down. Now, basically, this is like throwing it up in the air and having it come back down, but it's like simulating a weak gravitational field. The first one to really use this technique was Galileo. He says, okay, hey, it's hard to measure things in free fall because the velocities were so high. So he goes, well, let's slow this down and simulate like a weaker gravitational field. Okay, give that a push, it's going to go up, whoop, come back down. Now, there's a couple of things that you need to decide as a group when you do this. You need to decide if you're going to go off the front of the cart or the back of the cart. I don't care which one that you go off of, okay? It makes me no difference. But you have to be consistent. So what you want to have in terms of data. So like Garrett's going to be in charge of watching where this thing goes up at the top, okay? Madeline might be in charge of watching where it is when I let go of it. So listen to me very carefully. Do not include the push, okay? Do not include the push. Do not include you stopping it at the end. So we're going to go from this very second I let go of it until it gets right back to this point, okay? Don't include the push or tapping it back down so it doesn't go that far. All right, so if you're going to go off the back, then Madeline needs to observe where the back of the cart is when I let go of it. Then if Garrett's watching up here, he has to watch where the back of the cart is. You can go off the front and the front. I don't care. Okay? It makes no difference, but you just have to decide which point you're going off of. Now, if you're clever, you're going to make the bottom of the ramp that marks 0. If you're clever, what are you going to make the bottom of the ramp where it says 0?
0.
Reference point. Oh, okay, right. Now, but what you have to watch is that when you let go of it, it might not be at the reference point, especially if you're going off the front of the cart. Okay? It's not a big deal. This isn't like, oh my God, what am I going to do? It's not a big deal. Okay, where's the cart? Okay, it's here. Okay, you're just not starting at the reference point. Okay, so don't flip out and go, oh, this is working. I wonder what to do. It's going to be okay. Not a big deal. Now, the other thing that you want to do is you want to have a couple people timing it. Oh, that was a good one. Yeah, that was varsity right there. And so you want to have a couple people timing it. Now, you're going to time it the entire time from the second that you let go of it until it gets back to that point. Don't time it on the way up and time it on the way down. You want to have 2 people timing the entire length of the track, because then we're just going to assume that it's symmetrical. And this is going to be a cool deal once we get into some more complex problems. If, and this is a huge if something goes up and comes back to the exact same point, you can assume that the flight has a symmetry to it, and the time up is going to be the same as the time down. But you can only do that if it returns back to that same point, and that's what we're going to set up here. So, to make things consistent, you're going to have positive velocity going up. So if we define this direction as being positive, the velocity has to be what coming back down? Negative. Does it change the direction?
No.
Okay. Now, so as soon as I push it, does it have a velocity vector?
Yes.
Yes. Now, as soon as it leaves my hand, there's 3 things that can happen to that velocity vector. What's one of them?
Stay the same.
It can stay the same. I could let go of it, and this thing would just keep going up at a constant velocity, which would be cool to watch. Okay? Not so much. So we know it's going to do something. So what's the other thing that could happen? The velocity vectors could get smaller. Okay? You think that's kind of where we're at?
Yeah.
Okay? Now, if the velocity vectors got bigger on the way up, what would happen? Yeah, it'd go faster and faster and faster, okay? Fire up the rocket engines, here we go, boys and girls, right? Okay? But the rocket, they frown on me firing rocket engines inside the building. I don't know why. I think it's cool, but anyway. Now, on the way down, what's going to happen? Velocity vectors get, but what else do they do? They change direction. So here's what you want to observe. What? You see the motion of the cart, oh, going up, slowing down, going back down, speeding up. So you know certain things have to happen. You know the velocity vectors have to change, right? Because they can't be the same going up as they are coming back down, or otherwise it wouldn't come back down, or it wouldn't slow down, or it wouldn't speed up. So you know the velocity vectors are changing. Do you think the cart ever has constant velocity? No, why?
It's always changing.
Yeah, it's always changing, right? Okay, so that's the deal. So let me hand out the lab so you can kind of see what we want in terms of data. So stop the camera for a second. All right, so you're going to give this thing a push, right? It's going to have a certain velocity vector. So at some point as this thing goes up, remember, there's three things that can happen. Velocity vector gets bigger, the velocity vector gets smaller, the velocity vector changes direction. On the way up, what's happening?
It's getting smaller.
It's smaller. So you can say, oh, here's V1, okay? And later on, you're going to draw V2. And then maybe later on, you're going to draw V3. And this is the type diagram I'm going to expect you to make in the course of the lab. If you want to show me and clearly indicate that these vectors are getting smaller, draw them so they're getting smaller. If you think they stay the same size, draw them where they are the same size. If you think they get bigger, draw them where they get bigger. Okay? So, going up, the velocity vectors are going to do what? They're going to get smaller. Now, did the cart accelerate on the way up?
Yes.
Now, remember, when the main reason I wrote this entire lab is to force you to understand acceleration, because that's the next unit. And the first thing I want you to get out of your minds, we've talked about this before, is the idea that acceleration means speeding up. Lock that out of your minds right now. What does acceleration mean? Change in velocity. It's the rate at which that velocity vector changes. That's it. Okay? It could mean it's speeding up, but it could also mean you are, it could also mean that you're turning. We'll get into turning later. Okay? So those are the main things that you have to look at, because any vector quantity has two components. What does it have?
Direction.
Magnitude and direction. If you're changing either one of those, you're accelerating. Okay? So when you turn your steering wheel, you're accelerating because you're changing the direction of that velocity vector. Okay. So when you're accelerating, your acceleration vectors can only point in one of two directions. It either points in the same direction as your velocity vectors, or they point in opposite direction of your velocity vectors. That's it. Nothing else in between. Now, here's the beauty of every acceleration problem you are going to study in the next 6 days. I only can spin acceleration problems in one of two ways, and one of two ways only. I can either make an object speed up, or I can make it slow down. That's it. I have a two-trick pony when I write this test. That's it. I can either make the car go faster, or I can make the car go slower. That's it. Okay? That is the only thing I can do. So, if you're told that something is slowing down, automatically, what do you know about the sign of velocity and acceleration?
They're opposite.
Opposite sign. If it's speeding up, you're going to have, literally, every acceleration problem that you have is going to play out one of two ways. Either velocity and acceleration have the same sign, or they have opposite signs. That's it. Okay? There is nothing else I can do. So always start with that premise. Oh, it's slowing down. They got to have opposite signs. Now, also get out of your minds that negative acceleration always means that you slow down. What's the only way that you can slow down with negative acceleration?
Positive velocity.
If you have positive velocity. Because if you have negative acceleration and negative velocity, you're going to speed up. So that's the other thing I want you to get out of your minds right now, that negative acceleration means you slow down. You could, but it's not an absolute. Okay, it is not an absolute. Okay, so let's say, for the sake of argument, that where you let go of it was 0.10 meters, and let's say when you got up to the top, it ended up at 1.10 meters. And let's say that the total time was 4.20 seconds. Okay, just to make up some numbers. So when you let go of it, you were down at the bottom of 0.1. You ended up at 1.1. Can you determine the displacement on the way up?
1.1 meters.
No. How do you calculate displacement? Final minus initial. What's your final position?
1.1.
What's your initial position?
0.1.
1. So what's your displacement?
1.
Okay, so on the way up, my displacement is going to be 1.1 minus 0.1, and I'm going to get 1 meter. Now, if the total time is 4.2, how long did it take to go up?
2.1.
2.1. So as long as it's symmetrical, the time up is going to be the same as the time down. Now here's my question. To get my velocity, could I take my displacement, which is 1 meter, and divide that by half the time, which is 2.10 meters, excuse me, 2.10 seconds, and call that my velocity? Could I do that?
It's your average.
Mary, you shake your head no, and you should. Why?
Because it's not a constant velocity.
Exactly. Look, this is the acceleration unit, okay? The only time you can take displacement and divide it by time is if you have constant velocity, okay? But guess what? What are we doing?
Changing the velocity.
We're changing the velocity. So if you ever find yourself trying to do this in this unit, unless I have explicitly, and I mean explicitly told you that something's under constant velocity, unless I have explicitly said that, if you find yourself doing this, stop. Get help, get an intervention. Okay? You cannot use this equation if you have accelerated motion. By the way, guess what this unit is? Acceleration. Odds are it's going to be speeding up and slowing down. So if you find yourself trying to take this displacement and divide it by time to get a velocity, stop. Okay? Stop. It's probably wrong. Okay. Now, but you're going, well, how fast was it going, Mr. Burkamp? I think, well, that's a valid question. But let's start with this. What's the position time graph going to look like for this thing as it goes up the ramp and comes back down? Hunter?
It's not going to start at 0.
It's not going to start at 0. In this case, it's going to start where?
Somewhere around
Yeah, 0.1 meters. Okay, right? Then what's it going to do?
It's losing velocity.
Yeah, well, let me give you a hint. There's 2.10, there's 4.20.
Down
Go down, like it,
until you get there,
okay,
and then go up.
to here.
Yeah.
Okay, why?
Because you have negative velocity, so you turn around and you get positive velocity.
But wouldn't I have positive velocity going up? Here's my question. At the end of 2.10 seconds, where am I at?
Top.
At the top, which we said was going to be 1.10 meters. Flip your graph over.
Yeah, you're right.
Because I'm going to start at 0.1, I'm going to end up at 1.1 up here. So we're going to go from 0.1 up to 1.1. Now, I'll give you all the multi-lip curve. Like, whoa, seriously, yeah, the multi-lip curve. So, one option is like that, a point, pretending that's 4.2. And then you got that. So you got curve A, curve B in the middle, and curve C, the multi-lip curve. So, bonding, A, B, or C?
A,
Why? You're right.
because it starts fast and goes slow.
And does it change direction?
Yes.
Yes. Does it show that?
Yes.
Yes. And then what does it do?
What?
After it changes direction, what does it
Back
do?
down to
Does it speed up?
oh, yes,
Does the line become steeper?
yes.
Ah, nice. Okay. So what's wrong with B?
Constant. And it's not constant.
Yeah, B would be kind of cool to watch because you would push it and it would go up at a constant velocity, then it would come back down at a constant velocity. Okay, cool, right? It's not what we observed. Now, the coolest one would be C. If C was right, what would it do?
Accelerate.
It starts slow, speed up as it goes up, and then it would start back down really, really fast, and then it would slow down right before it got to your hand. Okay? C would be the cool one to watch. Okay? Because like, boom, right? Okay? But that doesn't match either. So, you got curve A. So one of the things you're going to do is you're going to draw a position time graph. This is what it's going to look like. Now, you don't know where it is at every point on the curve, but you know the general shape of the curve, right? You know halfway through it's going to be at its maximum height. It's going to come back down at the entire time. So this is all you have to do is make a sketch. It's just a sketch. Okay, now, and it's what Vonda said. I'm going to start off with a big positive velocity. That's going to become more shallow. Up at the top, my velocity goes to 0. And then it's going to change sign and become negative and speed back up. Now, let's talk the velocity time graph. But at this point, you all are really going to flip out because you're going, how are we supposed to draw the velocity time graph? We don't know what the initial velocity is. You just said we couldn't find the velocity by taking displacement in time. What are we supposed to do? Valid point. Okay, but let's start with some curves. So here is 2.10 seconds, and here's 4.20 seconds. So there's curve A. There's B. And there's C. So you got A, B, and C. So here's my question. Which one is the right velocity time graph?
C.
I'm thinking B. I'm thinking A.
How many vote A? 1, 2. Okay? How many vote boring B?
I'm wrong.
Okay?
It's B.
How many vote curvy C? Okay?
Yeah.
Mad Max, why are you wrong?
Because that's a curved line for the velocity, and it's the same acceleration through the whole thing, even if it's like not with the same direction as the velocity. So it's the same constant acceleration, so it's going to show constant slope.
So, for those of you that voted for A or C, I blame Nike. Okay? It's Nike's fault for this misconception. Because Nike says, oh, you've got to have movement, you've got to have swooshes, right? Okay? Because here's the deal. Go back to a simple definition. What does the slope of a velocity time graph give you?
Acceleration.
Acceleration, right? So if you voted for A or C, you're telling me that the acceleration changed. Okay, that's what you're saying. The acceleration changed. Now, let's think this through, start to finish. Very first day you were in this class, we talked about that big red sign in the back that says F equals ma, right? We've talked about this, F equals ma. So here's the $1 million question. Is the mass going to change as that cart rolls up the hill?
No.
Pretty constant. Don't drop an elephant on it halfway through. Okay, that'd be awkward. Okay, and that just getting the elephant in the room. Now, what's causing the force?
Gravity.
Gravity is, right? Gravity is a good thing, okay? We have gravity in the universe, it's a good thing. So, do you think the force of gravity is changing as it rolls up the hill versus rolling down the hill?
No.
No. So if the force isn't changing, and the mass isn't changing, guess what?
Acceleration doesn't change.
Acceleration isn't changing. So that only leaves us with which curve?
B.
Middle one. It's boring, okay? There's this speeding up and we're slowing down and we set up swooshes, okay? No, swooshes implies that force of gravity changes, and it doesn't in this case, okay? It remains pretty uniform. So what we should have is this boring line that looks like this. Now, at this point, you're going to flip out and go, Mr. Burkamp, we don't know what the initial velocity is. You're right, we don't. But we're going to get clever and we're going to find it. Now, let's play Name That Shape. This looks surprisingly like a
Right
triangle, right? Area of a triangle is
Base times height divided by 2.
1/2 base times height. True? Everybody cool with that? It's like, oh, I've never seen that before. That's cool. Okay, yeah, that's right. Now, this is where we're going to get clever. Do you know the value of the base of this triangle?
Yes.
Half the time, right? That's cool. Okay. Now, do you know the area of the triangle?
Yes.
Displacement.
Mary, how do we know the area of the triangle?
Displacement.
Oh, we know the displacement because we know how far the cart went up. Oh, so we got that now. So here's the $1 million question. What does H represent?
Your initial.
My initial velocity. So we find the initial velocity by looking at the area of a triangle and knowing that displacement equals the area. So now, y'all are running with the big dogs at this point. You're not in Algebra 1. I need to get H by itself. So what do you, if you're me, and I hate fractions, what are you going to do?
Multiply by 2, divide
Multiply
by
by?
2.
Divide by?
B.
Yeah, so is that so tough? Oh, that's simple. 2A divided by B is going to equal H. So in this case, I'm going to take my displacement, which we said was 1 meter. So I'm going to take 2 times 1 meter. Now, the base is going to be half my time, which is going to be 2.10 seconds. Ah, conveniently, what units do I get? Meters per second. Oh, how cool is that? Which is going to represent our
Initial velocity.
Ooh, that's cool. So this is going to be about 1 meter per second. So now I know this point. At this point, could you find your acceleration?
Yeah.
Shively, could I find the acceleration?
Yeah.
By doing what? No, you don't know the force. You don't know this point on the line, 0 and whatever, about 1 meter per second. I want to know this point on the line, which is going to be 0 and 2.10 seconds. So if I know 2 points, I can find,
Slope.
which gives me my
Acceleration.
beautiful. Okay? Now, very first day you were all in this class, we talked about this. That A equals V minus V naught over time. Now, here's where you're going to get clever again. We're going to look at this as 2 distinct paths. One on the way up and one on the way down. On the way up, what's your final velocity?
0.
0, because it's going to stop. My final velocity is going to be 0. My initial velocity is going to be some positive number. So if I take 0 minus some positive number, I get, divided by a positive time, gets me negative acceleration, which matches with what we said here. Okay? We should end up with a negative acceleration. Okay? Now, on the way down, okay, on the way down, what's my initial velocity?
0.
0. So on the way down, my initial velocity is 0. But what's my final velocity going to be? Some negative number, right? So then we're going to have a negative number minus 0 divided by time, which is also going to get me
Negative acceleration.
which is why this velocity time graph has
Negative
same
slope.
slope. Okay? Now, we have the same slope here because we have the same force, which is creating the same acceleration. Okay? Makes sense. We're all good. Okay, we're all good. All right. So here's the data that you're going to need. Now, notice down here on number 6, I say, answer the questions below and include all numeric values in every calculation. You don't have to do very many calculations, okay? Basically, the displacement is the only one that you need to calculate. I know y'all can divide time in half. Don't write that down. I'm just worried about like the actual displacement calculations. That's the only one that you have to show. Now, on here, as you go through this, you're going to need the angle. Call me over. I'm going to take my phone, and I've got a digital readout, and I'll give you the angle. Okay? That'll be the easiest data that you have to collect. And then your total time, I'd have a couple people timing it. Now, if one person times it and they get like 4.2 seconds and somebody else times it and they get like 4.8 seconds, that's too big a gap. Oh, we'll just take the average. No, somebody was clearly wrong. Okay? So when you're timing it, make sure that those times are relatively close together. If there's a big discrepancy, do that again. So you're going to record the initial position of where this thing is when you let go of it. Again, I don't care what you go off of. The front, the back, I don't care. It doesn't make me any difference. Just make sure everybody in your group is aware of the point that you're going off of. So you got total time, boom, here you go. Now, over on page 2, there's question number 21. In about 2 weeks, you'll see where this equation comes from. But to get the theoretical value for your acceleration, this is like a perfectly frictionless inclined plane. You've got A equals negative 9.8 meters per second squared times the sine of the angle. So, like typically your angle is going to be about 2 degrees. So you take the sine of 2 degrees, multiply that by negative 9.8, that's your theoretical acceleration. Okay, that's what you should get. Okay, if it's perfectly frictionless, that should be your acceleration. Now, over on that last page, I want you to calculate the experimental error. This is on your equation sheet, but I want to make sure everybody's cool with experimental error. So it's an absolute value of your theoretical minus your experimental divided by your theoretical multiplied by 100. So basically what you're going to do is that you're going to take your answer to number 17 and your answer from number 21 and then divide that by the answer to number 21. Everybody's data is going to be different. Pay attention to the negative signs. You're going to have a whole bunch of negative signs within this, but it's an absolute value. Show me the numbers because everybody's is different. When you get to question number 22, or 23, excuse me. So here's the setup. There's the cart. You want to draw velocity vectors and acceleration vectors on the way up, and velocity and acceleration vectors on the way down. If you want me to think that the velocity or the acceleration vectors change, you draw them clearly so that I can see that they change. If you think they're the same, you take a ruler and you draw them the exact same length. Now, don't make this difficult. Here's your cart. Which direction on the way up do you think the velocity vectors are going to point?
To the right. Up.
Up, right? So here's number 23. Here's the thing. The first thing you're going to do is draw a velocity vector like this and go, oh, there's V1. Don't point it straight up. The cart isn't going straight up. It's rolling up the ramp. Okay? Don't draw it straight up. Now, from there, you're going to draw a V2 and you're going to draw a V3. If you think they're changing, draw them where they're changing. Then with the acceleration vectors, draw them where they're changing, draw them where they're staying the same. I don't care. Pick one. When you get to question number 25, this is the full-blown acceleration one with gravity. So what's happening on 25, you're going to take a ball, you're going to throw it up in the air, and you're going to time it from the time that you let go of it until that it lands back in your hand. Total flight time is 2 seconds, and it goes up to a height of like 5 meters. 5 meters is about twice as high as the ceiling, so to give you kind of some perspective. So on that one on 25, you're going to do the exact same technique that you did on the lab. Okay, it's the exact same technique. If you're not sure what to do, go back, look at the map. Okay, I'm done. So tomorrow we will not meet, sadly. So this is gonna be due on Wednesday, okay? We're good. Now, and I can slice some more, but I bought a bunch of lemons, it's French. If you're into the water thing, I've got some lemons, so if you want to freshen up your water, I've got some sliced lemons. There's a couple there. I can slice more lemons. I bought like a whole bag full of them. Anybody want some more lemons for their water? You're all in on the water? Okay, on the lemon water? Okay, just remember that. We'll throw a couple quarters in, help us save the world. So, okay, go be free. You're on your own.